a bit like a science lab. Understanding the science of cooking helps you make food taste as it should. So why does food behave as it does when we cook it? And what's going on in our head when we eat it? In this episode, the chemistry of meat, buying it, storing it, cooking it and cutting it, you'll see some super sensitive high-tech equipment that can track flavour molecules, and you'll learn how to revolutionise the way that you cook meat at home. This is a top-quality Aberdeen Angus bull, prime meat. We can see the muscle along the backbone with very little connective tissue. That's the fillet. It doesn't do much work. It's very lean and tender, and we use this for fillet steak. The shin muscle here has to be connected up to the bones with lots of strands of connective tissue. It does a lot of work. It's very tough. Muscle runs right through the tail. It's joined to the bones in the tail with lots of connective tissue. It's very tough and also full of fat. And the chemistry of cooking meat varies according to the cut that you buy. This is Newett's Butchers in Thame, near Oxford. I used to come here when I was 16 or 17. It was my training ground for learning about meat, and it's where I get my meat from now for the restaurant. Every cut is traceable. You know where it's from, when it was slaughtered, how long it was hung for. So I know we're cooking the best meat I can possibly get hold of. Hi Tom, how are you?
Yeah, very well, thanks Heston. Nice to see you.
Yeah, good, you too. I've got some important experiments I need to do. So I need to order some meat from you, please.
OK. What sort of things have you got in mind?
Can I have 4 ribeyes beef, ribeye steak, exactly the same thickness?
OK. About 14 ounces in size?
Something like that, yeah.
OK. What about that?
Yeah, that's good.
There, Heston, how's that for you? That's the first 2.
No, they look lovely, don't they? Cracking. Really nice marbling of fat and very low connective tissue on here. These have come from the eye of the meat running along the rib, along the back of the animal, so it's not done much work. Across, yeah. For the other half of the experiment I have in mind, I get 4 shin steaks. Yeah, that'd be great.
OK.
As you can see on these pieces, an awful lot of connective tissue here interspersed with some fat. It's come from the shins, done an awful lot of work, and that collagen needs to be broken down. And finally, a rib of beef.
All right. So, Heston, very nice to see you.
That's great.
Best of luck with your experiments.
That'll keep me busy for some time, that's for sure.
You'll have to bring us in a sample of your lamb. We'd like to try that at some stage.
OK, great. OK, I'll speak to you soon.
All right,
thanks. Tom. Bye.
Okay, bye-bye.
Now, let's see how these different cuts react to being cooked at different temperatures and whether browning meat seals in the flavour. The most commonly heard statement in the kitchen is that browning the meat seals in the juices. What a load of rubbish. I can't believe the amount of times I've heard it or read it. Now, I'm going to show you an experiment that will demonstrate how completely ridiculous this statement is. Here I've got Peter Barham, physicist, who hopefully is going to explain a little bit more in depth the chemistry of meat cookery.
Yep, that's the idea. But first of all, let's start by exploding the myth that browning seals anything in. OK. So what's the plan? We're going to cook those steaks?
Yeah, I thought one of the easiest ways to do this was simply take the weight of the steak before cooking, take the weight of the steak after cooking. Yep. Cook 4 pieces of steak at 4 different temperatures, and we'll have a look at them. Each steak is weighed, then cooked to different temperatures. I'm going to be flipping these every 15 to 20 seconds.
We can hear now hissing away. Every time they're hissing, something's coming out. That's steam coming out, so we know that they're not sealed. Water's coming out of them all the time.
I think we'll start probing now. This is a piece of equipment every kitchen should have. A digital probe thermometer to check the temperature inside whatever you're cooking. Steak 1's taken off at 40 Celsius. It's lost 25 grams. Okay. Steak 2's taken off at 50. It's lost 38 grams. Steak 3 at 60. It's lost 63 grams. And steak 4 at 70 Celsius, the brownest of the lot, it's lost 85 grams.
It's absolutely swimming.
Look at this.
And I suspect if you squeeze it, even more will come out, actually, Heston. What we can see is that browning does not seal anything in, because all of them have lost weight.
They've all been browned?
They've all been browned. The one that's been most brown's lost the most weight by quite a long way, 85 grams in 320 grams. That's over a quarter of its weight's been lost by being cooked.
The thing I find amazing is the amount of times you hear that on television, you read it in a book, in a recipe in a magazine. Oh, I'm just going to seal my meat. They might not even say I'm browning the meat to seal in the juices. It's now been abbreviated to the line, I'm going to seal the meat.
Yeah, there's no way that you sealed anything into that by browning. In fact, by heating it up, you're squeezing water out of it. It's the opposite of sealing. So I suppose the next thing is to try tasting a minute and see what the effective temperature on the inside has.
Yep. Then we tasted them one by one. Ribeye steaks are low collagen, low connective tissue. Above 40 Celsius, the meat starts to shrink a bit. At 70, it shrinks and hardens irretrievably. You'll know why when you see what's happening to the molecules. Here are the protein molecules in the lean meat. As they harden above 60 Celsius, they bunch up and squeeze out all of those lovely juices. Which is why steak 4, cooked the longest, was the greyest, toughest and driest. Now this... Oh, look at that.
That is meat for my mother-in-law. That is thoroughly unpleasant.
It actually's got the texture of a doormat. Not that I've ever eaten one, but...
Yeah, but I wouldn't... Yeah, that's the sort of meat you wouldn't want to feed to any good friends. No.
How differently do high collagen shin steaks react to heat? We place these in a special cooking bath that controls the water temperature and cook them to 40, 50, 60 and 70 Celsius for about 5 hours. This meat only starts to soften and become edible at 60 to 65. But why? Here are some tough old triple helix molecules of collagen, the ones that hold the muscle together. Heated above 60, they unravel into their separate parts, softening your meat. Which is why, even after 5 hours, the collagen in steak 1, cooked at 40, was still indigestably tough. Look at that. It's not particularly soft. I think it would probably snap if I pulled it, but it's pretty hard. You wouldn't be wanting to eat that. And the collagen in steak 4, cooked at 70, was just as it should be. All of that, you can see all of that lovely connective tissue there. It's all started to open up and soften. And if I just move this apart, it should come apart very easily. There, look. That's lovely. Look at that. I think this demonstrates just how important it is to cook this meat with high connective tissue for a long period of time. So all of that tough tissue gelatinizes and turns the meat into the lovely, juicy texture that we're looking for. So next time you go to your local butcher's or to a big food hall like this one at Harrods, remember the chemistry of meat. Everything you see here, steaks, sausages, poultry, hams, is changing at molecular level all of the time. Heat it and the change speeds up. And as we've seen, the molecules in the different cuts react differently to heat. In fact, there's chemistry all around you in a place like this. For example, why is red meat red and white meat white? Again, the answer lies in the molecules. The difference between red and white meat is most marked when you cook it. Here's Harold McGee, who wrote a book on the science of food which changed my life.
The color comes from a particular molecule called myoglobin, and it's a relative of the molecule in our blood that makes our blood red. And both of them have the same job, which is to store oxygen. And the amount of myoglobin that you find in a muscle, and so the color of that muscle, depends on how hard and how long that muscle has to work. So here in the chicken breast, which has basically no color at all, the reason there's no color there is that the muscle is hardly ever used. The chicken does a lot of standing around and very little flying. And so we all know that chicken legs are rather dark. That's the dark meat of the bird. The breast meat is the white meat because the breast muscle is never used. In the case of the pigeon breast, pigeons are capable of flying hundreds of miles without stopping, so they need a tremendous amount of oxygen storage capacity in their muscle to fuel that kind of exercise, and so that's why the pigeon muscle is so deep red.
Here's how we serve pigeon at the restaurant, the fat duck. First, the pigeon pastilla, with cherries, duck stock and spices. The pigeon, cooked at 54 Celsius for half an hour. Small crisp turnips, cooked in water and butter. Some halves of caramelized onions. some cocoa nibs with pistachios, cooked off with some honey, spices, salt, pepper and sugar. And finally, the sauce, a pistachio veloute. And there it is, pigeon as we serve it at the Fat Duck. And now for the chicken. Strips of celeriac and celery, braised in their own broth. The chicken breast poached at 63 Celsius for just under an hour. Celery and celeriac sauce, made from the braising liquid infused with tonka bean. And to finish, a bit of decadence. Freshly grated black truffle. Coming up, a strange set of chemical reactions that the scientists themselves don't fully understand. Every few weeks at the Fat Duck, I discuss kitchen chemistry with all my chefs and trainees. That's one way I pass on what I know, but it's not how I learnt. I taught myself. I did 12 years of experiments on every dish in classical cuisine before I ever opened the restaurant. That's how I learned how to cook meat. So we've seen the temperature range required to cook pieces of meat with low collagen in, and we've also seen the temperature range required to soften the collagen in pieces of meat with higher collagen in it. Now here I've got a rib of beef. Now this cut of meat's got relatively low collagen or connective tissue, so we cook it at the lower temperature range, 50, 55 degrees centigrade. I'm going to throw a spanner in the works now. We need to get those lovely roasting flavours that we all like when we roast joints of meat. How do we get that? And that only comes about when we cross another temperature threshold, around about 140 degrees centigrade. Now, the problem there is 140 is an awful lot higher than the temperature that we want the inside of the meat to get to. So we've got a bit of a problem. To get round that problem, we blowtorch the outside before roasting, without overcooking the meat inside in the way we saw earlier. It might look a bit strange, but it works. The butane gas flamethrower instantly heats the surface of the rib to well over 140 Celsius, producing those roast meaty flavours we're after. The lean, low collagen meat inside will then cook slowly in the oven at about 55, so it doesn't dry out. The so-called Maillard reactions occur above around 140 Celsius. Proteins and carbohydrates react with each other, make new chemical combinations that then fall apart again, and form other new ones. It's so complex that even scientists don't know exactly what's going on. But the upshot is that the hundreds of different flavour molecules are created, some flying off the surface of the meat. Result, that wonderful roast meat aroma. So the rib's going in a roasting tray, bone side against the tray to protect it. Okay, oven thermometer in the tray to make sure that we know the temperature all the time. Preparing the side vegetables with me, Harold McGee, the man who changed my life as a chef when he wrote that science shows how browning the meat does not seal in the flavour. That started me on the road to kitchen chemistry. So why did Harold decide to write about the science of food?
I thought writing about the science of everyday life would be the most interesting sort of thing. Black holes and exotic things like that are fascinating, but I thought that everyday life had really been ignored, and that there were pretty amazing things going on in our own kitchens, and not just in exploding galaxies. So I decided to find what was interesting and useful about what was happening in the kitchen. But one of the things I didn't realize at the time was that chefs weren't taught the scientific approach to cooking, even though cooking is essentially chemistry. It's applied chemistry, and I think was probably the original chemistry. Before anyone knew anything else, they had to make food that was safe to eat and easier to eat. So I think the first chemists on Earth were cooks. I actually thought that chefs didn't need to know this. And it was a huge surprise to me when I started getting letters from people in the business saying that this was something they'd never been taught, and it was important to them because it helped them understand how traditional techniques work and sometimes how they don't work. And then it freed them up to think about new ways of doing things.
Learning kitchen chemistry has certainly transformed the way I cook. The temperature's now at 42 degrees centigrade, so we've got about 10 degrees to go till it's ready. I think that'll be about another hour. It's been in for 4 hours, so it's a good 5 hours cooking time. But the important thing is the oven's at a very low temperature, very close to the temperature that we're going to be serving the meat at. Right. Right, some 5 hours later. Yeah, it's pretty good.
It's beautiful. But I guess the proof is going to be when you cut it open. We'll have to see.
Most people don't realise how important it is to cut the meat in the right direction. Actually cutting across, across the fibres instead of through them. Here's one slice cut through the fibre and one cut along it.
And you can see that here you have lots of long, intact fibres that you're going to have to chew through in order to break it down in your mouth. Whereas here, you've got lots and lots of little pieces already.
Comes apart, doesn't it?
Oh, yeah. Oh, that's going to be tender.
Simple rustic fare served with side vegetables, topped off with a beef juice and marrowbone sauce, full of natural flavours. But what is flavour, and how do we perceive it? Next stop for some cutting-edge flavour science, Geneva, Switzerland. If you want to find out about the science of flavour, this is one of the best places to come, Geneva. This is Firmenich, one of the world's leading manufacturers of synthetic flavours. I visit whenever I can to discuss kitchen chemistry with the scientists here. We're in the Rhone Valley, a place with a long tradition of synthesising food and science. The valley's full of vineyards. In the nearby Jura Mountains, Louis Pasteur had labs and studied winemaking. There are over 250 scientists researching here. At the hub of it all, the new Food and Flavour Expertise Centre, where they've developed a vast range of new synthetic flavours, even boiled beef. This for me is like being a child in a toy shop, a really big toy shop as well. It's better than that. So many ideas that come up when you're smelling these things. So I see one thing and then I might get distracted because I see something else. So I think I need to be locked in here for a couple of days. The chemists here are at the cutting edge of the science of flavour and use some of the most advanced technology on Earth. Using a technique known as mass spectrometry, they can even measure many of the molecules that give a particular food its flavour. This mass spectrometry machine takes samples of my breath from my nose as I eat. It then tracks the flavour molecules as they send signals about flavour to my brain. So, for the first time ever, we can compare what's really there with what I'm perceiving.
So, just make you comfortable on the nose piece, put it slightly in the nostril, and then just breathe in and out. And we will register just your breath pattern for the first 3 or 4 times, and then I give you just one chewing gum. Just put the chewing gum in your mouth and start chewing.
Once I start chewing, I can read out the flavour molecules passing up into my nose. The green is menthol and the red is menthone. The volatile flavour molecules, menthol and menthone, fly out of my mouth and up into my nose. The molecules fly up to the top of my nose and hit nerves which then send electrical signals to my brain, and I register the flavour of chewing gum. Now comes the strange part. I'm still chewing, the flavour molecules are still being released, tracked and registered, but I can't taste it anymore. The computer is registering exactly the same concentration of flavour in my nose that was there when I first put the gum in my mouth. But taste-wise, it's all but disappeared. The longer we eat something, the more it seems the brain just gets bored by the flavour and switches off, telling us it's not there when in fact it still is. So what does this all mean for the chef? Well, for me it means a bigger menu consisting of exciting little courses. And where meat's concerned, that meat dish within itself has to be exciting. It has to have an unusual combination of flavours, overlying flavours, so the brain and the palate don't get bored of what they're eating. Now for something special. Now, this dish takes far too long for most of us to try at home. It also involves some equipment which is pretty hard to get hold of. But it perfectly embodies what we've been talking about so far. This dish involves 5 different lamb preparations. The core of the dish is the saddle, which is cooked at a very low temperature. This makes for unbelievably tender meat. The downside, however, is we lose those lovely browning, roasting flavours that we love so much. So we get over this by incorporating those back into the sauce. Now my head chef Gary is going to prepare this for you. First, remove the lamb fillets from the bone. The panufla, the meat that runs along the ribs, is set aside for crackling. Place the fillets in a backpack bag, together with garlic, bay leaf, thyme, rosemary and olive oil. Seal the bag in a vac pack machine. Most butchers have one, but if you can't arrange this, marinate it as normal. Place the sealed bag in a fridge to marinate. Meanwhile, to make the lamb sauce, we lightly brown diced lamb shoulder, enough to give us the desired Maillard roasted meat flavours. Not too much or we make the sauce too salty. You just want an evenly browned flavour. Next, sauté some sliced carrots to add sweetness. After around 10 minutes, add finely sliced onion and star anise, which accentuates the meaty flavour. Keep cooking till it's lightly coloured, then add this to the diced lamb. Deglaze the pan by adding a little cold water. Reduce to a syrup, stirring all the time. Repeat 4 or 5 times until the pan's clear of residue. Then add this to your lamb and vegetables. Then add cold water, just enough to cover the meat, and simmer for up to 90 minutes. Later this is strained and reduced to a sauce. Discarding all the herb marinade, seal the lamb fillets in new bags. Then cook in a water bath at 55 to 60 Celsius for an hour or so, until the internal temperature reaches about 55, maximising the flavour. If you don't have a water bath, you could use a slow cooker with a temperature gauge. Now the plating up. First, a line of onion puree. Then a tomato filled with this puree. Some green beans cooked with grey mustard and a touch of cream. Then the sliced lamb fillet. Some cubes of sautéed lamb tongue. Next, the sauce. And finally, a square of lamb crackling. And there you are, saddle of lamb cooked at low temperature.